We are starting on page 542. So this is the last lesson of Module 4, Topic 1, Lesson 3. So we're going to be reviewing next and then taking our Module and Topic 1 test. So this is a pretty small topic, so that's why we're taking a test so soon from our previous one. It was just 3 to 4 lessons. But anyways, on this lesson, we're focusing on activity 3 and talk the talk, and this is on cubes and cube roots. So last lesson we were talking about squares and square roots, so similar, but we're just kind of adding another layer to it. So looking at this beginning part, cubes, right? We talked about cubes earlier in their like physical shape, but also what do they represent, right? They represent 3 numbers that are being multiplied. They have factor 3 times that are equal. So this example here, we're looking at the volume of 125, right? This would be 5 times 5 times 5, which is 125. So that would be that side dimension. Here are our key vocabulary terms, cube root. So a cube root is one of 3 equal factors, meaning they're the same number. As with the square root, the cube root uses a radical symbol, but it has an index of 3. So what does that mean? We were just focused on square roots, right? These are all called radicals, but let's say square root of 4. Right, right, the 4 is a radicand, right? This is a radical, but we call this a square root sometimes. The index, though, the index isn't shown here, but in a square root, the index, there's like an invisible 2 there. Typically, we don't write that. It's just implied that there is a 2 because we're looking for 2 numbers, 2 factors that equal 4, and that's coincidentally also 2 because 2 times 2 is 4. But when we have a cube root, we would say that the index of this is 3. We're looking for 3 numbers that if you multiply it together, so like cube root of 125 is 5 because 5 times 5 times 5 equals that. All right. So it says the index is the number above and to the left of the radical to indicate the root you're calculating. If you're using a calculator here, like if you Google calculator on your Chromebook, you're not going to be able to find an operator for cube roots. Typically, you would use a scientific calculator, but actually we've already done these. So number 1, it says write the cube root for each perfect cube. So this would read, A would read cube root of 1, B would read cube root of 8. And we've actually already done this. If we go back a couple of pages, let me see if I can find it. It was the one that we had for right here, for where we had a side length in 1 dimension, a square in 2 dimensions, and a cube in 3 dimensions. So where we wrote these numbers here of 1, 8, 27, so on, this is where we're multiplying 3 numbers, right? 2 times 2 times 2, 3 times 3 times 3, and you get the idea. These numbers are going to help us for the page that we're helping or working on, but let's go back to that. Okay, so cube root of 1 is 1. If you look back at the previous page, or that past page, cube root of 8 is 2 because 2 times 2 times 2, I'll do this off to the right, is 8, right? 2 times 2 is 4, 4 times 2 is 8. Cube root of 27 is 3 because 3 times 3 times 3, right? 3 times 3 is 9, 9 times 3, that's where we get 27. But as you can see here, right, the pattern that we have, 1, 2, 3, just increasing by 1 unit. So the cube root of 64 is just 4. And really everything is just increasing by 1. So the next one should be 5. And we found that off to the right here. Cube root of 125 is 5. Next one is 6. This one is 7. 8. Cube root of 729 is 9. And cube root of 1000 is 10. Okay. So we're going to answer some of these questions following this. So we're going to need this list to help us. So we'll be referring back to this quite a bit. So number 2, what is the side length of the largest cube you can create with 729 cubes? So imagine like a big cube made up of, right, 729 cubes. what is the side length of it, right? What is the length and width and height, right? Those are all equal. This would be, looking at I, this would be 9 cubes or 9 units for the side length. Number 3, will the cube root of a whole number always be a whole number? Now, that should be no, right? For these ones, yes. But like, if you look at A and B, cube root of 1 and cube root of 8, everything in between that is not a perfect whole number, right? That's cube root of 2, cube root of 3, cube root of 4. None of that would be a whole number because you couldn't make a perfect cube from that. Meaning, let me do my best job to draw. I'm going to draw 2 cubes here. This is 1. This is 2. Let's draw this. Okay. If I were to put that side by side, that doesn't make a perfect cube because this is, right, it's got to be the same length, same width, same height. This is technically a 2 by 1 by 1. And if you notice, those 3 numbers are not the same number. It would have to be a 1 by 1 by 1 or 2 by 2 by 2. So that, no. So we just say no, it will not always be. Will not always be a whole number. And most likely it won't be a whole number. Like if you look at it, the cube root from 1 all the way to cube root 1000, there's only 10 of them that are perfect whole cubes. So, I mean, 10, I mean, if you, well, let's just subtract. 1,000 minus 10 is 990. There's 990 non-whole number irrational cubes. There's only 10 from 1 to 1,000. So the chance of that happening, very unlikely. So we're going to go through the next page and right, just like we did for perfect squares, where we at least can estimate. Okay. So it says most numbers do not have whole numbers for their cube. We're going to estimate those. So our example here, I'll highlight this. What is the cube root of 33? Before we get to that, let's actually write out the answers on our number line. We know that cube root of 1 is equal to 1. Cube root of 8 is equal to 2. And we actually already have these ones filled out. Cube root of 27 is equal to 3. Cube root of 64 is equal to 4. And I'll finish up on cube root of 125 is equal to 5. Okay. So for our example here, cube root of 33, what we're doing is we're using that list that we made earlier and trying to figure out what's it in between. It's in between cube root of 27 and cube root of 64, right? Which is equal to 3, and cube root of 64 is 4. So we know that it's in between 3 and 4, so it's got to be 3 point something. At this point, just like we did for the last one, you're trying to figure out, right, how far is this number from these other numbers here? Because maybe it's not directly in between. Like this, how far are those numbers away? This looks like it's 6. And cube root from 33 to 64, that would be not quite 30, it would be 31. So this is a lot closer to cube root of 27, right? It's only 6 away versus cube root of 64 is 31 away. So although this number looks like it's like kind of in between, I would say that this number, where the dot's right there, it's got to be more, draw this circle, it's got to be more right here, since it's that much closer to 3. So this has got to be a 3 point, and think of a number that's really close to 3. Right here, as you can see, we would say that it's 3.2. So what we did, we multiplied 3.2 by itself 3 times, 3.2 times 3.2 times 3.2. This is, we could think about this as $32.76 or 77 cents. And then 3.3 is $35.93 or 94 cents. So which one of these is closer to our problem, which is 33? Looks like this one definitely closer. It's only a couple cents off. to be $33. So we would say when we estimate, it's about 3.2. And if we look at our problem, what we circled, let me erase this right here. I'm going to put an arrow from there. Yeah, I would say that number is probably close to 3.2. Okay, so there's quite a bit of estimation in that one, but it's about using, right, those perfect cubes that we made in the list prior. All right, looking at the bottom of page 534, it says, right, there's a fact about cubes that is not true for square roots. If you remember, when we have a negative square, there's no way it can equal a whole number or just an irrational number. It just doesn't compute. When you put that into your calculator, right, if you remember from last time, it said error, but it is possible to have a negative for a cube root. So in the example here is that negative 5 is the cube root of negative 125, because negative 5 times negative 5 times negative 5, well, a negative times a negative is a positive, and a positive times a negative is negative. So it's possible for us to have negative 125. Okay, so just keep that in mind. All right, let's go to the next page, finishing up activity 3, and then we'll get to talk the talk, where we'll spend the majority of our time on. So number 4, identify the two closest perfect cubes, one greater than the radicand and one less than the radicand. That's where we're finding it in between. Then locate the approximation of each expression of a number of the line. We're going to do a couple of these. Let's say we're not going to do each one of these. I'm going to be referring back to my list. So let's look at 100, cube root of 100. Let's go back to right here. 100 is in between, right? The closest one below it is 64. Closest one above it is 125. And that is 4 and 5. So it's got to be 4 point something. So so just remember that 64, 125. Okay. So cube root of 64 and cube root of 125. I'm going to write what they're equal to just below it, right? This is 4 and this is 5. So we know it's 4 point something. We just got to figure out what that something is. How far are these two numbers away? It looks like that's 36. These two numbers away, 100 to 125 is 25. So this has a shorter distance to 5, not by much. So this is probably, I would say it's like a little bit over 4.5, let's say 4.6. All right, so 4.6, let's go ahead and put that on here. So let's say 4.6 on the number line, probably somewhere right here, closer to 5, not by much. Let's say that is the cube root of 100, which is about 4.6. Okay. And let's go through one more. I'll leave this last one as a you do. Let's go to 175. So 175, which one is in between or surrounding 175? So 175, it looks like 125 and 216. So let's remember that, 125, 216. 125, 216. Okay, just like we did here, we're going to write them. Cube root of 125, which we know what that's equal to, 5. Cube root of 216, which is 6. So it's in between 5 and 6, but what is it closer to? These two numbers are 50 away. These two numbers, what's that, 25 plus 16, so 35, that's 41 away. So it's only 41 away from this, so this is closer to 6. So not that much closer, so it would be between 5 and 6, so this has got to be 5 point, looks like we're going to end with another 6 in our tens place. So let's put 5.6 here, right? If this is 5.5, 5.6 is probably somewhere right there. Okay. Let's go ahead and put for this. This is approximately square or cube root of 175. which is about 5.6. Okay. All right, and then let's go and move on to, so C is a U-do. Let's go to number 5. All right, to answer this, determine the side length of each cube given its volume. So we know that a volume of 27 cubic feet just means, what's the cube root of 27? That is on our list, it's 3. So we'll just say it's 3 feet. For cube root of 31, we don't have that, but that's in between. I'm not going to go back to the list, but that's in between cube root of 27, which is 3, and cube root of 64, which is 4. This is a lot closer to 27, so this is probably going to be like 3.1. If it's cubic inches, then this will be 3.1 inches. All right, and then the last one, this is on our list, cube root of 512. If you go back to that list, 512, that's got to be like 6. Oh no, it's 8. Cube root of 512 is 8. 8 times 8 times 8 will equal that. So we're going to put 8. If it's cubic yards, then this is just 8 yards. 8 times 8 times 8 will give us the cube. All right. So this is going to sum it up for cubes and cube roots, but we're going to go to talk the talk. We're not going to do all of these, but let's do a couple of them to determine where they go. So what we have here, we're going to be going back and forth between 545 and 46 and putting these numbers where we think they should go. But for right now, this is combining the set of rational numbers, so all the things that can be represented by fractions, and the set of irrational numbers produces the real number system. Okay, we're gonna use the Venn diagram to describe these numbers. Let's do these numbers, but let's do the first. There's 5 rows. Let's only do the first 3 rows. So I'm gonna cut these ones out. Okay. Number 2, use the Venn diagram to decide whether each statement is true or false. So before we get to these questions, we're going to have to go to the next page, which is the real number system. On the left side, we have rational numbers. And then, if you remember, we created a smaller diagram earlier, right? This is comprised of integers and then whole numbers and natural numbers. Off to the right, this is everything else, irrational numbers. And I put a little bit of a description here, so there's no terminating decimals. I put terminating should be terminating. There's no pattern, and it's decimal and cannot be a fraction. So what we're going to do is we're going to take these numbers. If some of these need to be simplified, we'll simplify it. But let's write the first one, negative 6.41. Where does that go? It's not a natural number because it's not a counting number. It's not a whole number. It's not an integer. It is this a rational number because it can be written as a fraction. The reason is you can write this as a fraction. This would be negative 6. The way you convert this is how you say the number, 4100, so it's 41 over 100. This is a mixed number, and a mixed number is a fraction. So we're going to put negative 6.41 or negative 6 and 4100ths in this blue area. Okay, let's go to the next one. This one can be simplified. This is equal to negative, and the square root of 9 is 3, right? Because 3 times 3 is 9. Right, it's fine if you have a negative in front of the radical. So negative 3, where does that go? You can see that's a part of an integer, so we're going to put not negative 3, but negative square root of 9, which is equal to negative 3. All right, let's keep it going. Negative square root of 2, this actually will be irrational. Let's look at our calculator here. I'll just put the square root part. Square root of 2. It is 1.41, and as you can see, this decimal doesn't repeat. It never terminates. There's no way to represent this as a fraction. So we're going to put negative square root of 2, irrational. The way I want you to think about this, these are the numbers that are like don't quite belong in the categories off to the left because it's not represented as a fraction. All right, next one. -1. Okay, right. -1 doesn't belong here, doesn't belong in whole numbers, it belongs in integer. We can see it right there. So -1. There's nothing else that we had to do to simplify that, so that's good. -2/3, that is written as a fraction. So we know anything that can be written as a fraction should go here unless it simplifies to be one of the other categories. So -2/3. All right, we have the first row complete. Let's go to the second. -3/8 doesn't simplify to be a whole number, so that will also be rational. -3/8. I'll just write it somewhere here. -3/10 as a decimal, so -0.3. Right, that can be written as a fraction because, right, -0.3 can be written as -3/10, and that's a fraction where we have a whole number as a numerator and denominator. 0, where does 0 go? So 0, it can be written as a fraction, but can we figure out a more specific category for it? I see 0 here for integer, but let's keep working through the list. I see 0 for whole number, but it's not a part of natural number. So 0 just goes here. Absolute value of 2. This means, right, when anything's an absolute value, it means how far it is away from 0. An absolute value of 2 is 2 away from 0. So it simplifies to be 2. So where does absolute value of 2 go? So I can see it right here in this list in integers and whole numbers, but that belongs in natural numbers. So we're going to put absolute value of 2, which is equal to 2. All right, a little bit past halfway. This is 0.01, so that 1 is in the thousandths place, so this is 1,000th. So that is going to go with rational. So 0.001, this is 1,000th. So that is a fraction. All right, let's work with our last list. As a percent, right, this is technically a decimal, but as a percent, in order to convert from percents to decimals, you do have to move this decimal to the left. So this is technically equal to 0.005. So 5,000ths. And 5,000ths is, right, like I said, just like this one, could be, what was it, 0.5? 0.5. Right, that will be, oh, sorry, 0.5. Okay, so just get rid of the 0 here, but this is rational. Can be written as a fraction. All right, this one we have a terminating decimal, and that can be written as 25/100ths. So that's rational. So 0.25. I'll put that here. All right, let's finish up this right here. Then we can plug this into our calculator for the radical. Square root of 25/100ths. So first, let's put 0.25. This simplifies to be 0.5. And we know that 0.5 is a terminating decimal, so that is rational. So we're going to put square root of 0.25 because that's equal to 0.5. That's rational because I can write that as 5/10, 5/10. All right, let's simplify our last two. This one here, cube or square root of 3/16. You can actually simplify when you have a square root of a fraction like this. This might look a little bit confusing, but if I write it like this, the square root of 9 is 3, square root of 16 is 4, and 3/4 is a fraction, so that means that this is rational. So let's put square roots of 9/16. And our very last one here, this one, it's a repeating decimal. And from the previous lesson, we talked about how repeating decimals are always rational. This would actually be, if you simplify this or plug it into your calculator, 91/99, this equals a repeating 91. So it would be 0.9191 infinitely. So let's put that as rational. 0.91 bar 91 hundredths. Okay, so we correctly put these numbers in their positions. We didn't do the last two rows, but you're more than welcome to do that as a you do. But let's go and answer some questions here. So for number 2, it says use the Venn diagram to decide whether each statement is true or false. Number 2A, a whole number is sometimes irrational. I mean, let's look at the irrational thing. Do we see any whole numbers? Nope, that doesn't seem fine to be a whole number. And as you can see, where it says whole number here, this pink region, that does not intersect the irrational section on the right. So this is false. Right, because that statement sometimes, no, it's never. So a whole number is never irrational. Okay. B, a real number is sometimes a rational number. Now, keep in mind a real number here and irrational. So, like, you're not going to learn this until you get to high school, but there's the real number system is what we just use typically from day to day. There are things that we will say are not real numbers. We're not using the context of like real being fake or the opposite of fake. It's just another kind of meaning to it. But I want you to keep in mind, right, this entire thing is the real number system. So back to B, a real number is sometimes rational. So keep in mind everything off to the left is rational, and that's a part of the entire real number system. So this is true. Right, a real number can be either rational, which means it can be written as a fraction, right? Or it can be irrational, which means it cannot be written as a fraction. Okay. And the last one, a whole number is sometimes an integer. So this pink region here, notice how that's in this orange region. So a whole number can be, right, so a number can be a whole number like this 0 here, but it can also be an integer. So the statement again, a whole number is always an integer. That's within this bigger group, so this is true. All right, so to kind of give a statement for us, like since we're, at Gibson, we have the house system, we could say like, an Amazaji student is always a part of Gibson Middle School. Yeah, that's true. I don't think there would be any other Amazaji students in other schools, but this would be true because that's a smaller group within a bigger group, right? So we would just say true. A whole number is always, so a whole number is always an integer. Right, because, right, whole numbers, right, that's the list, right, 0, 1, 2, 3. That's always going to be a part, or I'm going to put in an integer, which is, right, put an ellipses, -2, -1, 0, 1, 2, 3. That's always going to be a part of this bigger list here. Okay. All right. Anyways, that's going to conclude the lesson. On our assignment for practice, we're completing all parts of numbers 1, 2, and 3. And this is on page 547. Okay, let me know if we have any questions.